Okay, hello everyone. In this video, we're going to actually be looking at how to use the pumping lemma to prove that a language is not regular. So this is going to be using the pumping lemma to prove that some language L is not regular. So how do we actually do that? Well, we saw that what the pumping lemma tells us is that if infinite regular language, then L satisfies some conditions, right? But if we take the contrapositive of that, right, so I'll just remind you, if we have a statement, if P, then Q, its contrapositive, which is logically equivalent, is if not Q, then not P. So we can use the contrapositive of the pumping lemma to say that if L does not satisfy the conditions of the pumping lemma, then L is not regular, okay? And so all we need to do now is we actually need to try to negate the conditions of the pumping lemma. So what are the conditions of the pumping lemma? So the conditions of the pumping lemma say, well, they say there exists an integer m, such that for every string there exists some decomposition, such that for every pumping up or down of that string will belong to L, right? So of course there's additional details like xy has to be of length at most m, and y has to have length greater or equal to 1. The length of w has to be greater or equal to m has to be a positive integer, and here I is greater or equal to 0. But the statement in terms of quantifiers looks like this, right? And so now what we need to do is we need to negate, if we label this star, we need to negate the star, right? So essentially we need to add a negation operator to there exists m for every w, there exists x, y, z for every x, y, I, z is an L, right? Well, hopefully you'll remember this from your discrete math class. If you have a negation on a sequence of quantifiers, right, then the rule here is to flip the quantifier from an existential to a universal, and a universal to an existential, and then negate the last statement here. So what I'm saying then is I'm saying to negate this, you would convert the first existential to a universal, the subsequent universal to an existential, again the same thing, and then negate the statement P. So what this looks like here, right, it says instead of there exists an m, it says for every m strictly greater than 0, right, there exists a w. Let's write there exists a w with length greater or equal to m, such that for every decomposition with the given characteristics, right, so with these two properties, that for every integer there exists a string where in each decomposition there is an I, right, there exists an I greater or equal to 0, such that, and now we negate this statement, right? We negate this statement which says x, y, I, z is not an L. And so to prove that a language is not regular, then what we need to do is we need to show that this statement is true. So the idea is that to prove L is not regular, we need to show that this guy is true, where this guy is assigned this statement. Okay. Okay, so how do we actually prove this statement, right? How do we, given a language, show something like this? Because this seems quite hairy, right? Um, well, it's not too bad if we sort of rephrase it or recast this as a type of game, right? So you have a game where you have an opponent and yourself, and you're obviously trying to win the game. So you're trying to defeat your opponent. And what your opponent is trying to do is it's trying its hardest to um, sort of sabotage your proof. Okay. And so what your opponent will do is your opponent will choose some integer m to which you have to reply with a move. So your move has to be picking a particular string. You have to pick a particular string with length greater or equal to m. You don't know what m is, right? So you have to base your string off this arbitrary m that your opponent picked. Okay. You create a particular string and you have to think ahead of time. You have to do some sort of counterfactual reasoning where you say, okay, my string has to be bulletproof, right? Meaning that for any decomposition that my opponent takes, right, for any decomposition that my opponent whips out, there's always going to be an integer I, there's always going to be an integer I, where when you pump the string that I initially chose, it's not going to be an L, right? That's going to be the game we're going to play. Okay, so what does that look like? Like I said, imagine you're in a game where you play against some opponent. The point of the game is obviously to win, to fool your opponent, where your opponent, you can also think of it as your opponent is trying to sabotage your proof. Okay? And so then the game follows these four moves, right? So move one is the opponent's move. That's because it's the for all that starts, right? It's the for all that starts, so you have to assume that you have some opponent that picks some, in this case, arbitrary positive integer, right? So the opponent chooses m greater than 0, which let's just specify is, let's use a different color, m is some integer, right? You have no knowledge of what this integer m could be other than it being an integer and it being positive, right? So in other words, you have to assume, you have to, let's write it like this. So you have to create a strategy for an arbitrary. Okay. Next, what you do is you pick a particular string, okay, where the condition that that string has to satisfy is that it has to have length at least m. Okay, so students typically have trouble picking a string. This just comes with practice, but it has to be a concrete string. So it has to be something like W is equal to, I don't know, AM B to M, let's say. Okay. It has to be a concrete sort of pen and paper written down string. So I'll write a concrete, tangible string. Next, it's your opponent's move. Okay, your opponent's move, what your opponent is trying to do is they're trying to decompose your string such that they defeat you, right? So how can your opponent defeat you is that they're very clever. They pick some decomposition where you can never find an I that when you pump it, the string doesn't belong to L, right? That's what your opponent is trying to do. So they're trying to use their best decomposition to fool you. Okay, and so then what you need to do, right? You need to assume an arbitrary decomposition. Okay, in other words, again, your strategy has to work for an arbitrary decomposition. Okay, so your opponent makes the decomposition move. Next, it's your move. Okay, so your move has to assume an arbitrary decomposition, and at that point, you have to pick a particular I. You have to pick a particular I for which, when you pump the string with I, that string is no longer an L. If you can find, if you can find such an I, then you win the game. You win the game, and by extension, and therefore prove L to be non-regular. Okay, that's the idea. So I have an exercise here, but I don't want to do that right now. Let's look at an example in the next video. But really what I want you to take away from this explanation is that what you're doing, right, is you're playing a game, okay? And there's very strict rules to follow when you play a game. So, namely, you can't decide what your opponent does, right? Your opponent is some genius you're playing across the table. You can't change their mind, okay? They're this very brilliant mathematician, okay? The only thing you could do is you could be more brilliant than them, right? And so to do that is you have to make your choice of string and your choice of I brilliant, right? They have to be exactly the right, suitable choices to derive really what you want is a contradiction, right? So, right, the contradiction being that the pumping lemma is not satisfied. Okay, so really make sure that you see, right? So the important takeaway here, the takeaway is knowing what you control and what you don't. That's really the most important thing. What you control and what you don't. Right? So you do control the choice of W and the choice of I, but you don't control how the string is decomposed and what M is, right? So it would be incorrect to say, suppose M is 17, and it would be incorrect to say, suppose X is epsilon, right? That would be incorrect. Okay. Okay, excellent. And so in the next video, we're going to look at an example. And I think the example is going to be a very familiar looking one.